I am here to tell you about something I hope will be of particular interest to the Wercker folks, and perhaps even what you might consider a bit of an open source offering. We very much would like to see Claire, that I will tell you about tonight, integrated into some other projects and products. We think it's quite versatily designed and pretty modular, and I'll try to explain a little bit about why that is and tell you what it is. So Claire, as my slide has kind of blown my punchline, is a container image security analyzer. It was, actually before I jump into Claire, I'm going to just do a little bit of background. How many people here use CoreOS? Can I skip most of that? All right, well, you know, atomically updated, automatically updated, cluster ready, lightweight, minimalist operating system based on pretty much today's latest Linux kernel. I think we just bumped to 4.5 like a couple of releases ago in alpha, so it's really up to date with security features and whatnot. We develop a large number of open source projects, of which I suspect you are also mostly familiar. Some of the highlights of those are Rocket, our container runtime engine. etcd, a distributed key value store that is itself already a key open source component of many other upper level projects, perhaps most famously Kubernetes itself. Pretty much anything that is stateful in Kubernetes ends up being stored in an etcd database that is a part of every Kubernetes installation. I like to say that we build and pursue all of these open source projects in the direction of a platform. A platform is their comprised, packaged, and enterprise supported form, a distribution of CoreOS and Kubernetes and many other tools that we call Tectonic. Along with Tectonic is a container registry that you may also have heard of called Quay. Now these are commercial products, and I'll jump right out of these and get into how they relate to the open source work very quickly. But Quay is a container registry implementing both versions of the Docker protocol, unlike the Docker Hub, implementing support for both Docker version 1 and 2 images, as well as app container images, ACI, our sort of competing, or let us say friendly cooperating image format that's attempting to drive a standard image format for doing all of this stuff industry-wide. And we think defining that container, what it looks like, and what its real specifications are is very important. AppC in the ACI format, Rocket itself as the runtime implementing those formats have all been in pursuit of that goal. So as part of Quay, we begin to take a look at the security of the containers we were storing for people. We do have a really interesting data set. Lots of people upload Docker containers. Developers of all ages, sizes, and skill levels upload Docker containers to Quay. And to start taking a look at the security vulnerabilities potentially contained in those containers and try to get a handle on what we were really storing in this container registry is the reason we built Claire. Claire is an open source tool and underpins all of the user level features and the graphical interface that's on top of things when you use the security scanning facilities at Quay on the containers you upload. So Claire, from a high level, it's a container image security analyzer. It does not implement heuristics in the style of antivirus scanners. It is based on a knowledge of the distribution, the packages from that distribution installed within a container, and the layer in that container with which a given package is associated and stored. So what it is really a response to what we see people really doing with containers, which is building them on a base of basically full-featured Linux distributions, despite what may be our best practices guidance about minimal containers, but that's another talk entirely. In response to that, we thought that the best way we could start figuring out some kind of a picture of the security within these things is actually just by going to known good sources, the upstream distributions, the operating system distributions on which these container from images are so often based. Then we built a tool around that idea and that knowledge of in-container packages and their vulnerabilities that you can query and send containers to along a really simple REST HTTP API. Which makes it both not only integratable because it's open source code, but also interoperable because it does have this kind of clean interface through which other programs can make calls to it and get results back out of it. Those results are really simple. They basically just constitute lists of vulnerabilities and an attached CVE number that matches them to the common vulnerabilities and exposures database. And we'll look at some of that in Quay screens and some Claire screens here in a moment. As I've already mentioned, this open source Apache licensed software is the basis of really important functionality in our commercial project. Our product, Quay. Quay itself does offer a free hosted version for individual open source developers, so these features are readily available to you. And if you have a big set of Docker containers, we invite you to upload them to Quay, where they will be automatically scanned by Claire, although I do not promise you'll like what you find out. And that's because of this. We live in an increasingly insecure world. We noticed two things. The number overall of vulnerabilities that are detected in this kind of funky but year-by-year chart, steadily growing and also subject to batching, we might call it, or sudden spikes. 2014 was a particularly bad year on this chart. This means that we have one vector of complication in the form of an increasing number of security vulnerabilities happening across all the software we might employ or deploy. Two, we've also made the situation worse. This is sort of what security looked like before containers. There was a clear line of demarcation of responsibility between the operating system layer, for which operations people were responsible, and which the libraries on which your applications depended lived, and the application layer, what developers had to worry about. What this meant, at least, is that a vulnerability in package C was fixed when package C was replaced at the operating system layer for all users dynamically linking that package or that library in an older world. Today, we're moving applications into containers. We're breaking their designs up into what we hope are good microservice and API boundaries. We're building nice modular components. But each of those components is partially modular because it imports and implements almost that entire operating system layer that used to live by itself and have somebody do it for you. So almost every container now has all the libraries, packages, or whatever the list of dependencies the applications running within it require. So that begins to look a little bit like this, and that's a simple high-level view, because when we really start thinking about it, what it means is we can fix package C in all kinds of places and still have it in stray containers that we don't necessarily have good control levels or control processes for, like what we build from, where we import containers. In a lot of Docker build chains, these are simply things we found on the internet. So, how common is this problem, really? We used Claire initially to examine the entire storage base of containers in the Quay registry. And we found some pretty interesting or terrifying things, depending how you want to look at it. I'm going to hit a couple of the highlight ones. These were kind of famous vulnerabilities. Ghost was a buffer overflow bug in get hostname functions that have been around in Unix system calls forever and ever, and really are implemented in the libc. When we ran Claire against all of the containers on Quay, we found that about 2/3 of them contained this bug, this vulnerability, which at the time was already about 1.5 years old. And we're not talking about things we found yesterday and then discovered in all of these container images and need to get them fixed in a hurry. We're talking about things that have been well known and out there for 18 months and still are affecting a huge number of these containers. Now, these numbers are roughly from Q4, really early Q1 2016. So this situation has actually improved such that the numbers are a little less impressive for the slides, and we think Claire has driven that improvement by flagging some of these things. However, at around the same time of investigation, we looked for an even more famous and perhaps even more dangerous bug called Heartbleed. This was in OpenSSL implementations. Affected wire security for all kinds of things using TLS to protect communications. We found Heartbleed in about 80% of all of the images that were on Quay.io in December and January. That's pretty bad, I think. I'm not a security guy, but it just seems like a bad deal. Why are these vulnerabilities so common? I've already touched on this a little bit, but this is really why. Almost all the containers really in use in the real world, even though it's not necessarily a good idea, and there are many better ways to construct your containers, are actually built from a really small number of common bases. And those bases contain a number of packages themselves, and when vulnerabilities appear, and everybody on Earth is building containers from CentOS or from Ubuntu images, that means everybody who's pulled this thing 29.5 million times is affected by whatever bug that lives in it. So how do we get a grasp on this and make it better for developers? We figured the only thing we could really do about it was provide a tool that gave some kind of automated detection of vulnerabilities. And we did have a choice to maybe go down a heuristics avenue and kind of build like a real scanner for these kinds of things. We think that would be both less reliable and potentially even less up to date, because it would rely on our ability to constantly, cleverly participate in the arms race of security. However, we can check every new image that gets pushed and every existing image every time the lists change against the vulnerability list exposed, published by operating system distributions. And I have a list of those. We'll talk about specific ones and how we add more a little bit later. So more than anything, we wanted to figure out that there were vulnerabilities in these images and provide some kind of notification to developers for them. Now, at an implementation level, we had a couple of concerns about that. We literally have to analyze millions of containers. We want to do two things. We want to do it very quickly with low commit of compute resources, and we also don't want to make ourselves vulnerable to anything nasty that we're finding in these containers. So these are the key points of the design at an implementation level, even though a very high level. We do not execute any of these containers as we look through information, as we look for vulnerabilities within them. What we do is extract everything we need to know about them from the static content of that container image, which if you really abstract a container image, it's a pretty simple thing that consists of some kind of a file system and a manifest describing how that file system goes together. Now, there are clever optimizations in the Docker image format, this layering idea, but they don't really change that high-level description very much. So, again, what is a container image? It's really two things. It's the metadata, what the base containers are, even things like who the authors are, ports that are exposed, all the stuff you do to configure a Docker container in a Docker file. And the file system diff changes from your base from packages to the things you've added on top of it. So this is what we're looking for when Claire scans container images. We try to identify the operating system. We have a couple well-known locations like the Etsy OS-release or other forms of the asterisk release name. There's app sources lists and the Debian way of describing this. These are all present in containers that are built from those base images, so they're available to us. At the same time, on these known operating systems, we then have known package listing locations. These are, what it looks like on Debian, what it looks like on most Fedora, Red Hat, or CentOS, or RHEL distributions. After looking through that, we map it into a graph-style database, which we'll talk about just a bit in the next slide or two, and we add a few things to it, so that we know a little bit more about the package. And so you can even think of Claire in many ways as kind of a general purpose container image analyzer that we have actually focused its initial feature set mostly on this idea of security analysis. We actually get a whole bunch of information about the whole construction and nature of a container image when we look at it with Claire. So once we extract all this data, we want to map it together and begin to understand the layers across multiple images that a from images vulnerability can then be propagated to vulnerabilities in containers built from it. Graph-style databases are a really convenient way to do this. You see this style of database used a lot to map like social network connections, who follows who. We actually want to do very much the same thing with vulnerabilities from a known list and map them through a set of containers. To do this, we actually use a bit of open source code from Google called Kaylee, which is kind of a cute name since you can describe these as Kaylee maps or Kaylee graphs in the first place after the mathematician who's sort of famously associated with them.
Not after Firefly?
Not so much, unfortunately. Maybe the other way around, though. I don't know. So anyway, we like Kaylee because it's written in Go. Almost everything we write at CoreOS is in Go, so it's much easier for us to adopt libraries and vendor code in one that's in a language we like. Claire itself is also written in Go. This gives us multiple backends for potential storage. We mostly use Postgres because that's kind of up and down our stack, our database of choice. Kaylee offers support for Bolt and MySQL and a number of other databases. There's even like an ephemeral in-memory version of it for testing, running it really quickly. So Kaylee helps us construct graphs that look a lot like this. Now, I'm going to run through some slides really quickly here such that when I'm speaking, they're going to look mostly like an animation, sort of what this graphing process and really what a Kaylee graph looks like, and we're going to build it out of some vulnerabilities. I'll hit a couple high points in it. I'm leaving all of these slides in this deck because it'll be available after I talk, and if you're really into this and you're looking at this at a developer level, you can go through this and kind of look at the fine print of the sequence of marching through this Kaylee graph with a vulnerability or two, and I think you'll have a clearer, more definite idea of what's going on. So what Claire does is, on one hand, it's a front end that extracts container image data, as we've looked at. Then it begins to map things we know about those containers into a graph database. Here, this is really small print, unfortunately, for my display size, but we do at least kind of have some color coding. Purple, blue, green, and red. This is sort of our container layer. Archives we're adding on top. Apps that we're actually building as developers. And then in the end, the red dots are going to represent vulnerabilities. The important thing here is that all these nodes are actually connected in these graphs. So like, you don't necessarily have to have a vulnerability. You could just trace a package all the way through a series of containers built from its source image. And there's some neat screens for doing that in Quay that we'll actually look at kind of in the closest thing to a demo I'll do here. But anyway, here we see we're building a container image from Ubuntu. So this first purple node, and I know this is super hard to see, I should have done these a little bit larger for where we are, but shows are from Ubuntu and version with the Docker label name Trusty, which gets you to like 1404 or whichever Ubuntu version that is. So basically, what you can see here is that same bit of data, that base image being carried through a set of containers as Claire analyzes them, breaks it down into, now we're at the green level and the purple level, the packages and applications we've added through package management commands, which we are, again, retrieving out of like the dpackage database in this case, because Ubuntu is a Debian distribution. What we're seeing here is a number of packages, and we are building towards what's probably a predictable punchline. We're looking at OpenSSL packages. And their rates of change across versions inside this Ubuntu version as they're upgraded from the distribution sources. So here we're looking at like a 1.121. Here we are looking at sorry, even I can't see that, so we won't worry too much about it. You will be able to see it if you look at the slides after the talk, probably. At any rate, what we're looking at is how we use Kaylee to build up these really nifty maps of what's going on inside containers. And I hope that that is more or less clear, because truly I don't think you have to understand the details of it to sort of get the general purposes of a talk of this length, but at a developer level, this is actually pretty interesting, clever stuff. You're building kind of network maps out of either vulnerabilities or just package contents within all of these Docker containers. So, what about those vulnerabilities? Well, in essence, those sort of graphs kind of show how we're going to work our way back to them, but here's a good idea of the things we're looking at right now when we do a Claire scan if you upload a Docker image right now tonight. We're going to try to identify its operating system, and to this list I would also add, we do have a basic understanding now of Alpine vulnerabilities. We're not 100%, like, it's not on the level and longevity of these three major releases, and so we're maybe a little less comfortable with it, but we do like the idea that people are building container images with Alpine, because if you're going to do a base Linux, at least let it be something really minimal. So at any rate, we have begun to look at their vulnerability data too. But we look at Ubuntu's CVE tracker, we look at Debian's security tracker, we look at Red Hat's errata list. Each of these things generally names the CVE, or Common Vulnerabilities and Exposures database, numbers of particular vulnerabilities and matches them to packages that hold these flaws. So that is exactly where we discover what vulnerabilities are contained in a given container image. So kind of looking at this graph again to kind of just walk through the same idea. Now we've identified a package, the OpenSSL package, with a vulnerability in it, right? So we can begin to see building the graph chain of the source Ubuntu from distribution up at the top right, where this actually originates, and mapping it back through the install package commands that added the OpenSSL libs to the version that originally introduced the vulnerability, to the latest version, which nevertheless still contains the vulnerability, and then at the far right to the version that would be the fix for this vulnerability. So what's this look like inside of Quay? What kind of interfaces can we build on top of it? So essentially, communicating with the HTTP API of Claire, Quay provides a set of user interfaces that look something like this. And I actually think it's probably a good time to abandon the slides momentarily and maybe show you.
Is that the Jenkins box?
Yeah, it actually is.
Yeah, fuck Jenkins.
Yeah, great. So this is funny that you bring this up, because I literally am in our repos, the internal CoreOS repos. I have a lot of containers that contain a single statically linked Go binary, and they're really not very interesting to look at on the security scanner because there's nothing in them, right? So I went looking. I thought, what's the biggest, fattest thing with just everything in it that you can't get away from it? And yeah, these Jenkins ones are excellent examples of things that still have a bunch of vulnerabilities in them. So this is actually my user account on Quay, and we have just, I'm looking at information derived from Claire scanning of a really large container with a whole bunch of junk in it. That's a Jenkins builder, I think, actually for a weird test we do at CoreOS for running Docker inside of Docker. But that's a whole different subject, right? But here's the point. Nevertheless, we can see at a high level what vulnerabilities have been identified here. And something new that we've added in very recent editions of both Claire supporting and underpinning this and the user interface offered at Quay itself is a lot more advice both about sorting or triaging these vulnerabilities, getting an idea about which ones are really critical and what sort of the size and type of the exposure is, because most of those databases that we're querying when we do this examination make that kind of info available. Is it a remote exposure or a local exposure? Is it a network accessible? Is it a root escalation? So we have a way of sort of sorting severities and helping administrators understand at least where they ought to focus their efforts. So looking down at some of these vulnerabilities in our giant Jenkins image, hopefully we won't still see heart rate, but we might in here. You know.
That Git one was it's a pain in the ass.
So
we just update all of our stuff to fix it.
Oh yeah, the second one down, the
Yeah.
Git bug you're talking about.
Yeah, prior to 273, the like arbitrary execution from checking something out.
Yeah,
Yeah.
that's cute. That's a
Yeah,
fun bug.
it's like-
I like that one. So yeah, this still exists in this set of packages. You know, and that's a bug we haven't addressed. Now these are ephemeral builders that probably live on our infrastructure for 4 minutes at a time. So you know, maybe not that important to us, but it does give us a good idea of what we kind of see here. We see a severity rating. Now some of these have numbers. Some of these, their source material doesn't offer us really a way to quantify it. And that's where you see these kind of high and low ratings. That basically means the upstream source on that bug doesn't give us enough specific information to sort of generate our little quanta number to rate these things. So actually, the neat thing that I wanted to show you here and really talk about is in Claire version 1 and its latest updates at Quay itself, you see this right-hand column with some good news for a change out of Claire, which you usually only get bad news from Claire. Claire begins using the same exact package inspection mechanisms to offer the upgrade path to the package that fixes that vulnerability that matches the operating system that is the from base image out of which your container was built. So you can see the latest updated packages that contain those fixes for packages that have fixes available. So this is a huge list of flaws. Now one of the things I wanted to talk about also is here we're sort of looking at things indexed or sorted on basis of their vulnerability. I mentioned Claire as potentially having general package analysis functionality, and this kind of hints at that idea. This is a look at the same vulnerabilities in the same container image, but sort of indexed or sorted on the idea of the packages in which those vulnerabilities occur rather than the vulnerabilities themselves. So, you know, it's basically just two different sorts looking at the same data, but this kind of shows you some of the other stuff that you can pull out of this, this kind of examination of container images. Once again, we have sort of summary ideas over on the right-hand side of like impact so that you can begin to triage and kind of figure out which of these things you ought to fix first. All right, so that's a little bit of a look at the Quay user interface that Claire supports. Those are two very hard words to say together. I encourage you all to grab an account on Quay. It is free, and it is a really easy way to just get started even exploring Claire, even if that's the part of it that you're interested in. And obviously it can give you a handle on sort of what vulnerabilities you're shipping in your containers.
We use it heavily.
Awesome.
And your IRC channel.
Yeah.
To basically answer any Docker questions we have.
Well, that's cool.
Which is
that is a place I always sort of forget to hang out. We use Slack so heavily internally now, and the IRC channels are great information sources, and like all the really smartest guys from CoreOS are always there, and I always forget to be there. So I self-select out of them.
Is Quay, I feel like it was largely in New York?
Yeah. Quay actually was an acquisition for CoreOS. Now they're well integrated in the company now. Quay's been at CoreOS a lot longer than I have. Kelly, I don't remember, like, you know, maybe 2 years ago in the acquisition, something like that. So in startup time, eons, and I'm very much a part of CoreOS. But Quay does comprise the largest portion of the staff of our New York offices, I believe. So yeah, there's a New York connection there. There also is unusually a Python connection here, which is a little bit rare for CoreOS. It is interesting, is largely trivial, and doesn't really make any difference, but we write almost everything in Go. We do have this one tool. Now Claire is in Go, but Quay and all of this infrastructure that supports both the hosted and on-premises enterprise versions of this Docker image repository is written in Python. So kind of interesting in the programming languages. One of the other things we do with it is provide some notifications. This is like at upload times. You just pushed a bunch of new containers. We'll notify you about vulnerabilities we found. Secondly, when package managers and upstream operating system distros publish new vulnerability lists, we already have a knowledge of all the packages that are in all of your containers. So we don't have to rescan them to update you about a vulnerability. If you have package A and Red Hat tells me tomorrow package A has a bug in it, then I know automatically that you're carrying that vulnerability until you upgrade package A to package 8.1. So those are the two sort of notification times that are cleverly implemented such that we don't spend millions of hours of CPU time scanning our base containers 400 times. Scan each container once, and are then able to update vulnerabilities in it efficiently for the future from there. All right, so that's basically it. I hope you enjoyed it. I really like, I do think that Claire is an excellent fit kind of into the worker stack. Like I think that's kind of would be a really neat component there to have on the front end of the pre-push side of doing that as part of a CI chain. And then, still having it it's sort of an upstream registry like Quay where it makes a lot of sense.
Just the insight into the packages alone is like pretty rad to have from
Exactly, which might be, because we focus so much on security as the feature set we were interested in first in doing this sort of vulnerability analysis, I think it's somewhere where I sort of expect or hope or want, like I hope that's a play, like I think a ready area for open source contribution and involvement with the Claire project is to begin to show its potential for being a general purpose analyzer of container structures, because you can do a lot of neat stuff with it beyond this, which is neat enough. I mean, this is probably job one, I'd agree, but. So we do have our major open source conference and festival. It's in Berlin this year on May 9th and 10th. If you don't jet across the Atlantic all of the time, I and a few of our other friends here in the San Francisco office will be speaking and hosting at a satellite event here in San Francisco on May the 9th. So I'd encourage you all to take a look at the website, grab a ticket, come out and see that. It won't be exactly this talk, I promise you that. This again is very much kind of for if you're interested and you look at these slides after the show, these will be some links that will be very helpful to you. This is the Claire repo on GitHub. This is a neat demo that Claire's primary designer, Quentin from the Quay staff, put together. That's a command line demo of running the HTTP API directly, which I didn't really show. Instead, I chose to show the UI kind of in the Quay features. But this will show you how to just take a container on your hard disk and then run the Claire container to examine it and get that same kind of breakout of information. All right. Oh, and the last link is how you can set this up spin it up on a Kubernetes cluster really easily. It's some simple instructions for spinning up like a minimal number of nodes in a Vagrant and having a K set to run Claire on, because that's kind of its natural native environments where we run it all the time. Thanks. Does anybody have any questions?
I have a question. The package system you're doing looks like it's like blacklist stuff, right? Like, so anytime you have a vulnerability, you get like a checksum or something for that vulnerability.
Yes.
Like 2 days ago, I think there was a gem, whatever the place that hosts gems is. They had somewhere like a bug for 2 years where someone could upload any gem under any file name, basically.
Right.
And now it's the best practice is you probably go through and like checksum all your stuff and make sure it matches, right? But you're not going to do that. So would you have like a whitelist kind of thing as well, where you could say all the packages and you say, hey, they should match checksums, so you don't have to go and do stuff like that?
It is not something that's currently implemented here, but it is certainly exactly the kind of thing I think would be interesting to begin building atop the sort of container inspection principle and capabilities that underlie this. So I mean, I would have a suspicion if I were going to try to like explore that from a design perspective that it could be tough to generalize that to a level where it would be useful, and like everybody wouldn't want to implement their own sort of whitelist, because I would think that would be pointed mostly at your own, the code your developers would be generating, correct? Like, so, I mean, it's an
more like
interesting idea.
upstream stuff that you have no control over. That, you know, they're like, oh, download this, check the checksums against it. Like, for instance, like Homebrew does it, right? It actually checks the checksum.
And then to just have it actually, like, you would declare that list of checksums and declare that that package was positive because it matched that list of checksums, as opposed to vulnerable because it matched some other list of target sums.
Yeah, I guess because you guys are like already identifying packages, you can notice when something's bad turns up from a big enough set of packages, right? Like, you obviously can't do that from some random package that I just developed. But
yeah, I don't know exactly what that sample, you know, the accurate sample size for that would be, but, you know, I would think we have pretty good knowledge of it based on, you know, I don't know the exact number of millions of containers stored on Quay, but it's a pretty significant number.
Yeah, it seems like you could kick people over the best practices pretty easily with that.
Yeah, well, I mean, this definitely did help a lot. Like, really something, if this were it occurs to me in the midst of doing this presentation that it would have been very neat to come back with like the comparative numbers to what we found in, say, December, January, and what we've done, you know, what we've been finding recently, like how we've reduced these numbers, so I could really talk about them in a statistical way. I know it's been significant, and so I do think from the blacklist side, there has been some pressure towards at least an initial idea of best practices there and moving people in the right direction. From the whitelist side, I don't know whether it's something the developers have thought about and discussed much. I haven't been involved in it. I think it's a neat idea. That's kind of the best answer I can give to that.
Cool.
How are distribution derivatives being handled, specifically Red Hat ones?
Where they have an available list of their own vulnerabilities, and where they have an individualized package vulnerability list that resembles the upstream sources, they either have been or can be added to Claire's list of known upstream vulnerability sources. I don't think we have done it for a huge number of derivatives, but it essentially amounts to modifying the parser, which this stuff in the Claire code base, this is fairly well abstracted. Because each of those, like we looked at a list of like 3 of them that are probably most important for us and we look at all the time, like Ubuntu and Debians and Red Hats. None of those 3 sources are in the same format or can be parsed and processed by the same, you know, front end. So the parser is fairly well abstracted, and like you would take the base one from Fedora and modify it if you wanted to. If your Fedora derivative has its own package list, then the Fedora parser would be the place to start. You would change it as needed to match their output format, and that's essentially how you would plug in a new source for Claire. And which is kind of when I was touching on implementing a little bit of that for the Alpine distribution. It's actually right in the heart of that issue, and why the Alpine scanner, the results of scanning Alpine containers is maybe not a first-class citizen on the order of the Ubuntu ones or the Red Hat ones yet, because we were not as certain about the source, the quality of the source, the frequency of updates of the source, and the long-term format of the source. So it was a little bit challenging for that one distro, because they're just a lot smaller than those other guys. Newer, like maybe a developer or 2. I'm not, sure of the whole core of the Alpine project. So they can be added, and I would hesitate to call it trivial to add new CVE or vulnerability sources, but it's also not very difficult. It has been part of the design has always been for it to be fairly easy to plug in new ones, because we knew there would never be like a standard interpreter for all of them, right?
Are you considering CentOS to be Red Hat? I can't imagine too many people are uploading actual Red Hat open source.
Oh yeah. It's definitely yes. Like Fedora and CentOS are probably like the ones that we actually see containers built out of all the time. Yeah, I mean, not that there's no RHEL in the whole container world, because there is, but yeah, very much. I just was saying Red Hat kind of umbrella term, right? Anybody else? All right. Thanks so much.
Deploying applications in a cloud-native world. What does that mean? Let's find out. How do you do next? There we go. So what is a cloud native world? So really, really loaded term. I think it's quite difficult. A cloud native world is a world that CoreOS wants. A cloud native world is containers, which are like little environments for your code, very, very small, deploying to schedulers like Kubernetes that kind of orchestrate your services all together. There's lots of moving parts. They're all talking to each other. You're not really worried about virtual machines or hardware abstractions. There's just, you just have your containers and your schedulers. You're deploying a lot, in some cases multiple times a day, which is, yeah, really a lot. And ultimately, like, your services should be like cattle, right? Like, you shouldn't really care if one service goes down. You should have like 10 others like hopping in to take its place. Like, that's the cloud native world. So you want to go cloud, oh, I skipped a slide. Okay, so let's take a little history lesson as to like how we came to the idea that containers and schedulers are a good idea in the first place. Because nobody just wakes up and says, yeah, you know, it'd be awesome if I made a container and like this concept is gonna be so good. So where did we start? We started with like PHP applications, kind of small, and we would FTP them up to a server, and then we would do something to start them. I don't know what this world was like. I was probably like 5. I mean, yeah, like 1998, I was actually 5. Okay, we've gotten some experience. Our applications got bigger, more complex. We start breaking them up into littler pieces, and we are like, oh, maybe we shouldn't just FTP all of our code into the server. That's probably a terrible idea. Maybe we should test. Maybe we should have some sort of pipeline process. And so our software got smaller, and we started developing CI. We started developing configuration management tools like Chef, and that kind of streamed a pipeline along. You ended up with an image, you pushed it up to AWS. And at the same time, you had the abstraction of, the same kind of abstraction on the hardware side. No longer did you have to go to the server rack store with a bunch of money and give them it. You can go on AWS now and get some server space. What a time to be alive. So yeah, you've got these, you've got smaller environments, you're breaking things up, and you have these wonderful tools. I like Jenkins. That test your code. You have. Get out! I mean, it's a good
Back
tool.
up your desk.
I guess I'm fired. Yeah. Yeah, you have this wonderful process. You like build something, you make an image, and you push it up. And now to the cloud native world. You've got little containers, little teeny tiny things. You have a lot of services, and hopefully they're all talking to each other. You want to deploy them to schedulers. And how do you do it? Let's find out. So you want to go cloud native. Let's talk about some of the pain points that you're going to have. So there's the idea of having to maintain different environments. I could imagine there's definitely a time, or like startups out there, who say things like, oh, it works on my machine, so it's probably going to work on the cloud, I hope. So they're just like, oh yeah, you know, all my code compiles, my tests work, and then they push it up to the server, and it's like, oh, it's like I wrote a Python 2 app, and the server guys put Python 3 on the environment. Like, what's going on here? So that was probably a time, yeah, once again, a time that I wasn't born in, or a time I never want to see.
It's still out there, buddy.
It's still out there. You do this, you should reconsider. Okay, then we start moving on. We're like, okay, we want some dev prod parity. We want our environments to be a little more similar. It could be better. What do we do? So someone really smart wrote Chef and Vagrant. and they're using Chef to make their Vagrant VMs. They're using Chef to configure their clouds, and you get a pretty similar environment. But every time I want to test my code, I have to do Vagrant up or something, and like run a bunch of commands and be in a Linux machine, and I don't want to do that. I like my Mac, spent a lot of money on it, very nice. But yeah, you have some dev prod parity, but it's very slow and kind of painful, and it's not what you want. It's not ideal. Ideally, you don't have to have a configuration Chef repository somewhere that like has all the configuration and the environment for your app. Ideally, your configuration should live as close to the code base as possible. That would make sense, right? Like, why would it be somewhere else? Yes, it does make sense. Thank you for agreeing with me, everyone. Okay, and then there's the whole deploy and release thing. So, yeah, there's people out there who still use programs like Fab. They still use programs like Fab, and they'll be like, oh, Fab deploy. And all of a sudden, my service, which Andy depends on, is entirely different. I never told Andy that I'm going to change it. I probably changed it because I want Andy to get fired. So now his service that talks to my service all different, and his service breaks. So there's no transparency, there's no nothing. Or even worse, you just push bad code. Like, there should be some sort of process. And so we start introducing that process. We have a little CI server. It tests our code. Then we produce an artifact. Then we use Chef or Puppet to kind of put that on AWS. And still, that's not cloud native. That's like still in the world of images, still in the world of VMs. You want something a little higher up, a little better of an abstraction. So you want something to test your containers. You want something to push your containers. Like, how would you do that? And so why the current model doesn't work for containers. Let's go on the next slide. So what people try doing now, or like as containers and projects like Kubernetes were introduced, they're like, oh, okay, well, I've got this pretty sick Jenkins server over here. I've got this super awesome like Chef automation stuff over here. Let me have my CI server, build a Docker file, then I'm going to use Chef to take that Docker file and push it up to Kubernetes. Chef doesn't really know how to deal with either of those things. Why the heck is Jenkins making a Docker container? Like, they're doing jobs they were never meant to do, right? So that doesn't make any sense. And also, look at how many points of failure there are. Someone needs to know about Jenkins, Docker, Chef, and Kubernetes. Does someone here know about all of those things? You don't know about them. You don't know about them. If you do, you're hired. You can have my job. It can be better. There is a beautiful future out there. And we can do all of this with Wercker. And hopefully, if my demo works, I will show you. I will show you this in action. So rather than having four different pieces, you'll have two. And that will just be Wercker, which will test your code and build it into a container. It will also push it up to a registry, and it will notify the scheduler to start your application. So, demo time. This Mac can't connect to iCloud.
Wait, you have a Yahoo address?
I thought you were
I'm learning a lot during this presentation.
Yahoo, he's dirty. You're a fucking time traveler.
I was just about to say, it's making me feel so old.
I'm very, very good at making people feel very old.
Next thing you know, I'm going to see like, you know, ICQ what is left.
Dude, ICQ, I hang out there all the time. Okay, so let's see what we got here. We have 3 different pipelines. The very first being a build pipeline. Since you need to build your code, you need a container that has Go installed, but ultimately you don't want to push that container up to the cloud. Like Josh was saying, you want small containers, right? So what we're going to do here in this build container is build a binary for us to use in the next pipeline. Is this big enough for you? Okay. Next poorly named pipeline is the deploy container. The deploy pipeline. Okay, so what this pipeline is going to do is it's going to take the binary from the build, it's going to put it into a busy box, and it's going to package it up, and it's going to push it to Quake with the tag foo, because why not? And lastly, there is going to be a step that I hope works called notify Kubernetes, which will download kubectl, and then it'll set this it'll start the app. It'll do a rolling update. So it'll pull down the image that I pushed up to here. That'll be done, and then it'll start the application, and hopefully I'll get to show it to you.
Did it work last time?
No.
As a side note, I realized recently we've fairly single-handedly made that Gox container, the GOX one, like the most popular Gox container on Docker Hub, because we use it like 50 fucking times a day to do all of our own builds. So it has by far the most pulls.
So yeah, so this bit you would have done with Jenkins, building and testing. This bit you would, and these last 2 bits you would have done with Chef or Puppet or whatever you use. But now we're just making it all into one, and hopefully I'll get to show you. So I don't actually know any HTML. I forgot most of it. So there's like an H1 or something, right? So what I'm going to do is I'm going to change the index.html to this web app that I have deployed here. What it does is it does a horizontal pixel sort on any image you give it. Makes a pretty little picture. Yeah, I'm into like glitch art and that kind of stuff. So I'm going to add a title, and its title is going to be foo. Okay, what's the title going to be? It's going to be foo.
Wow.
Rackspace startup.
It's going to be Rackspace rules in league speak. And I'm going to run all 3 of those pipelines. So the first one is building the artifacts, which is the Go binary. The second one is pushing to Quay, and the very last one is the one that hopefully is going to notify the Kubernetes scheduler to work. And if it doesn't work, it's definitely not my fault. It's someone else's. So this is pushing up to Quay with the tag foo, because why not? Now it's installing.
Like half of those are high vulnerabilities. I can tell.
Yeah. So we're installing curl to install kubectl on an Ubuntu box, and yeah, those are probably super insecure. You know, what's the fun in having secure stuff?
Updating Chinese certificates.
Okay, now it's starting the scaling process. I hope this works. If it doesn't work, I'm real sad. But this is the bit that's notifying the scheduler. This is starting up a Kubernetes what's it called, Matt? It's a service or something?
Yeah.
No, it's not a service. It's like you can rolling update it. I don't
You've
know
got
what it's
a
called.
exact-
isn't it?
Huh?
Isn't it a replication controller?
Well, a replication controller makes multiple services. I don't know what this is.
Well, no. So we've got an RC and a service, but what we're doing is we're rebuilding the RC to have a new image. Although, Spike, you have an exec format error.
Oh, cool.
So you must have changed something.
Well, it will certainly fail. But yeah. But the point here is pretty powerful, right? We built an image. No, we built a binary. We put that into a container. And then we notified Kubernetes. I mean, it ultimately did that. The container was messed up. That was my fault. But we did that with one command through Wercker. So that's my presentation.
Wait, so if you do that in production and then the container's messed up, will it just go down then?
You know,
We're
that's,
using a rolling update, so no.
yeah.
But
that's-
the one instance will eat shit though, right?
Well, I think what it'll do is it'll spin up another one. It'll
Yeah.
notice that one is not good,
Uh,
and so it won't take down the previous one.
Okay.
It's just like ECS.
Yeah, alright, gotcha.
Yeah, there's a bunch of like Kubernetes operational stuff that I don't necessarily know the ins and outs of
Yet,
yet.
Yeah.
Is the keyword there. But yeah, rather than having the point here is clear though. You don't want 5 different things working all together like very loosely. You kind of want one very clear process behind everything. Yeah, thanks.
Hi, friends. So yeah, my name's Greg. I'm the CTO at a new AWS, hot new AWS monitoring startup called Opti. So I was not 5 in the year 2000 when all of this was, happening and the dot-com boom happened and the wonderful industry you are now profiting from was created. I was there. So yeah, I'm here because I'm super jazzed about containers. I'm a big CoreOS fan, I'm a big Wercker fan, and I do have to apologize to the Wercker people who are so graciously hosting me. That I did not really know Wercker when I started building everything at OPSI, so we don't use Wercker, but we are. Yes, no, and that is a big yeah. So a lot of this stuff will sound a little bit familiar because we basically recreated Wercker, but like a really janky version of it that we're not super happy with. But it works, right? So yeah, so why Docker at OPSI? Partially, I love containers. The cool thing about containers to me is the actual image itself. Being able to build the exact object that will be deployed in production locally on my laptop and knowing that like what I'm using right there is exactly what will be in production. And like it may not be configured the same, it may not start out the same, but like that, it is that thing, that binary is exactly what will be there. That kind of predictability is incredibly important in software engineering, right? Like we really need to understand what's being deployed and where. So Docker at OPSI, and I know that this picture gets a lot of play with Docker, but Docker at OPSI has been a little bit of a bumpy ride, right? Because the lovely thing about containers is that it's incredibly new, and as like engineer number 1 at a hot new AWS monitoring startup called OPSI, just back there being like, yeah. I get to like greenfield a lot of stuff, and so I was like, you know what, I have been dying to just Docker everything up from the ground up forever. I'm gonna go whole hog. So the problem with doing this, of course, is that adopting any new, like sufficiently new and complex technology takes a considerable amount of time and effort and energy and resources. So not only does it like take you time to go, okay, this is the new technology, this is how it will break, blah, 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 blah. Like you're gonna make mistakes in all of your assumptions about how it operates. You're gonna make mistakes in all of your error correcting along the way. And you're gonna learn from them, but again, it just takes time and a lot of patience.
for example, believing that what they say they're going to do is what they're doing.
Yeah.
Yeah.
So, as far as Docker in production goes, we're going to talk about three main things, and that's building software for containers, because it's different than building software for D packages. It's different than building software for golden image AMIs that you're rolling out. It's different for building ancient PHP applications that you FTP to web servers.
Did people really do that?
Yeah, people really, I think people still, I still really do that. Yeah, yeah.
Runs on WordPress.
Yeah, exactly. WordPress. So yeah, after that we'll talk about kind of like how we're going to deploy these new fancy good containers, and then like operational considerations that you don't really think about when you start using something like Docker. So the number one thing that I think I've learned in a year of production containers is you want thin containers. You want the smallest possible deployables that you can have. It's kind of like when everybody was packaging these enormous JVM apps and you had like 1.2 gigabyte, jar files, and you're like, yeah, I mean, this is the company. We're gonna SCP this company around to every single one of our production servers, and then we're gonna start the JVM. Well, like the problem with that was that you spent all of your time SCPing stuff, and you had to build these enormous jars, and it took like an entire day to get everything rolled up for deploy, which is why we only deployed once a week. And actually, less than just a few years ago, I worked for a company who would only have downtime once a month scheduled for every client, and it would take anywhere between 12 and 24 hours to actually do a deploy. So, I mean, this is very much still reality. People still are doing these huge, enormous fat deployments. So thin containers, even if you're deploying a bunch more containers, it's going to be a lot faster. Just because we're building smaller deployable objects, they're going to build faster, they're going to ship faster. And yeah, if you have thin containers, you're going to end up with a lot less operational problems like running out of inodes and running out of disk space. So, avoid operating system containers. We use Alpine Linux for everything. Docker is moving to that for their official base container. They were doing Ubuntu, now they're going to Alpine Linux, which should make adoption of Alpine Linux at more of these like Quay with the Claire and stuff. I would assume it's on their roadmap at this point. You don't want really shells in your runtime images. They're a crutch, basically. I have them in my runtime images specifically because I wanted a crutch. I was not comfortable with containers. I was not comfortable with Docker. I didn't really know what I was doing, and I wanted to be able to get in and Docker exec. I wanted to make sure that what was in the container is what I expected to be in the container. But when you first start using a tool, you don't just inherently trust that it's going to do what it says it's going to do. Like there's a certain trust that has to be built into that contract that a tool like Docker has with you, and it takes time. So yeah, you want to avoid OS containers. You want to avoid Byzantine startup scripts, and Kelsey Hightower actually goes into this a lot on Twitter, and he will rant about startup scripts a lot, and I wholeheartedly agree with him. We have horrible startup scripts in all of our containers, and they make it incredibly difficult to run containers locally on the desktop because we've actually optimized for production at this point, and it's kind of holding us back. So runtime dependencies should go in volumes, actually. So our startup scripts pull configuration from S3 in production, like straight up curl, or we use KMS, and we have a little tool called S3 KMS that actually decrypts it and pulls it.
What's KMS?
Key Management Service in AWS. So
AWS KMS.
Yeah, AWS KMS. So I can say this instance has access to use this encryption key. So when it pulls something from S3, it can actually decrypt it, and that's how we limit who has access to what configuration. So at runtime, it actually calls this command S3 KMS, pulls down the configuration, and then it's just an environment file. So it's literally ./config and exports it to the environment, and we start up and read it all from the environment, which is horrible, but we wanted to make it easy to run it locally, so you would just export all of your configuration to environment variables in your Docker run, or use an environment file locally, and it turns out that this is horrible and not easy and was not a good idea. So we'll talk about other ways to do that in a second. So the thing to remember is that if you have thin containers, and if you don't have operating systems, and if you don't have shells, containers actually cost very little. So the S3 KMS binary that we have is, I think, 1 or 2 megs. That could just be its own container. It could be used to initialize a data volume, and then we could link to that from another container to get configuration in production. And then actually do something completely different on your desktop, because what does it matter how you get configuration in production? We just need to make it easier to run these things on our laptop. So if you're going to have these thin runtime containers, you need to have a corresponding fat build container, right? Like you need a shell, you need to be able to write your build scripts, you need to be able to run make, you need a Go, you need a C compiler, you need libc or libmusl, whatever you want. So all of that goes into build containers. These are completely separate from the containers that you run in production. And this is
Not muscle?
musl, musl.
I don't know either.
I like music, so I say musl, because reasons. So yeah.
I call it exec format error.
I support it on Patreon, okay? No, yeah. So libmusl. Oh, yeah. So why we use Alpine Linux in both places also is because we don't statically link our Go binaries either, because we're bad citizens. And so we link against libmusl in our build containers and then use the exact same Alpine Linux container for runtime, so the linking works. So yeah, that's how we get around that. And yeah, runtime runners, they're just, runtime containers are just for running things. It's where your binaries go, and that's it. So this is what I was talking about on how you can just get configuration in a data volume and then link to it from another container. This is like good practice. This is what we should be doing and what we're not doing, but this is what we're moving to because it makes way more sense. And you can even just deploy this to production in Kubernetes or ECS with Docker Compose files. And we'll talk about that in a second too. So back to the crunch, right? I wanted to be able to get into containers and see things like artifacts that containers were generating inside themselves, right? So when we were getting our configuration, I wanted to be able to get in and say, oh, are we actually getting the correct configuration here? There are easier ways to do that, right? So if we just put things in a volume on the host file system, then I can just get on the host and look at it. And actually this is what we've moved to on our Bastion, which is our little instance that we deploy in your environment. There are several things exported to the host file system so that for support we can go in and look and say, okay, this is its configuration, this is its OpenVPN log, this is stuff that we're not exporting to like our log, central logging and stuff. So yeah, if you need to get things out of containers, like we've been doing this in production forever. We ship things to S3, we FTP to places, we commit to Git repositories, we put things in NFS, we put things in Ceph. We emit metrics, we log. There are a lot of ways to get stuff out of containers. You don't need people SSHing to machines and Docker execing into their containers. That's just not good. And eventually, it's going to get to the point where there are no machines to SSH into because people will just be running containers. I think Joyent is making really good progress with this. I think Tectonic's making good progress with this. You're not running VMs. You're saying, I'm going to run these things on Kubernetes, on a cluster I don't manage, Google Compute, all these things. So get used to not being able to Docker exec into your containers. Deploying. So the 3 big pieces to deploying containers are registries, images and tags, and schedulers. Depending on registries really sucks. This is one of the biggest problems we ran into over the past year is when your registries go down, you are down. You can't deploy unless you do some really fun stuff like exporting images, SCPing them over to machines, importing them, and then doing Docker run, which I've done before. You have to figure out ways to get around it, and you need to just build to your container registries will go down. They'll be unavailable, and that needs to not halt operations for your organization. And I think that CoreOS, I think that Docker, I think that AWS now with the EC2 container registry, I think these people understand that they are really in the critical path to production. And like, when we first started using Quay, well, when we first started using Docker Hub, it was a total nightmare. We got off it very quickly. This was before the move to Docker 2, or the Hub, like Registry 2 protocol or whatever. And before I think they really beefed up their support for Docker Hub. But just with the small number of containers we had like a 30 to 40% failure rate pushing and pulling from the repository. And I don't know if that was just, maybe I'm doing something wrong. But we moved off to Quay and we had much less downtime, but even still, there's downtime, right? So you have to really think about what happens when the registry is not there. And this is me. When there's registry downtime, I get really cranky and really angry and I start screaming at people who shouldn't be screamed at.
Just start making more coffee.
Yeah, pretty much. I go away. I just walk away from it. So yeah, downtime can and will happen. So one of the things that we've figured out is Docker and systemd both. So we use Docker restart policies in one place and we use systemd restart policies in another place because we have two very different ways of running containers. We have the Bastion, which is like this little self-contained thing, and it's a kitten, and it doesn't do much besides like get deployed and then run things. And then we have our back end, which is all EC2 container service. It's a lot more dynamic. Things get scheduled wherever they're going to get scheduled, and so we kind of rely on this Docker restart policy, where if a container goes down, you can have the option of saying, hey, Docker, just restart this when it fails. So the nice thing about this is that if you've already pulled the image, it will be there and it will restart. If you let your scheduler move it to another machine and it tries to start it and the registry's down, you now have a permanently down node in your replication controller that you can't correct. So that's one thing. In systemd, we just don't fail on Docker pull. So you have this little dash after the equal sign in your systemd thing, and it says, hey, if you can't do this, just keep going. So you can restart. So one of the big things that I noticed Docker espouses is symbolic tags for containers. This is like the worst practice I've ever seen with Docker containers. Just a very trivial example. Let's say you have your org, your service, production, right? And your CI service builds a container, and whenever it's gone through all the CI steps, it gets tagged production. And then maybe you're not just ready, maybe you don't do continuous delivery like we don't, because we don't always want to build and deploy all the time. Maybe you do push to your registry then. So now you have a thing running in your production environment that when your container dies, is going to restart it, possibly pulling from a container registry your image before it starts it, like Kubernetes would, or ECS would, or Mesosphere would, or anything. So now you have your old production tag over here that's still running, and your new production tag over here that's still running, and they're both behind the same ELB, or load balancer, or whatever. And now they respond in different ways. Now you have introduced non-deterministic behavior to your API, and you have pissed off your front-end developer, and nobody's happy with you. So the way that we've kind of gotten around this is we actually just tag with git SHAs, which is really effective because it's a very clear visual indicator of exactly what code is running in your container at that time. There is no better way that I've seen to do this. If you want to manage semver stuff for humans, you can. I hate automating that crap, so we just use the git SHA as our tag and push to repositories that way, and very deliberately deploy git SHAs. And that has saved us from more than one downtime now, I think.
We're using build IDs.
Yeah.
So it's like the actual product that got created at that one thing that you can go inspect again later on.
I saw that in his little deploy thing there at the end. I was like, yes, awesome. So yeah, that's good. But seriously, I'd just like to reiterate this point. I promise that using symbolic container tags is bad. So just don't.
Always push the latest.
Oh yeah, latest. Just use latest. Just use
The greatest idea Docker ever had.
the worst idea anyone has ever had. So the third component, right, to running containers in production, and one of the components to running containers in production is schedulers. Most of them are really good. A lot of the ones that are out there are really good. Some of them are easier to use, and some of them are harder to use. And I think that's really the biggest distinction between any of them, is their ease of use and their operational complexity. So also, of course, there are features like Kubernetes has a ton of stuff built into it. It's very modular. There are tons of plugins. You can do all kinds of stuff with it. Its operational complexity is loads beyond any of the SaaS offerings. It was one of the first things that we looked at because, again, first engineer, greenfielding, really want to use all the new shiny stuff. But ended up just saying, like, nope, I'm not going to have to run services to run my services. So yeah, we ended up going with ECS, and we like it. But most importantly, don't just consider operational complexity and feature, but like, what are you actually trying to do with containers? How are you trying to deploy? What are your specific needs? So one of my favorite things that a lot of the schedulers are doing right now is saying, hey, this Docker Compose thing is actually kind of rad. And I think it's brilliant, it's great. Containers work well together. Being able to say, this is my tiny service, and it actually just runs with these things. Like, we use NSQ quite a bit. And we might deploy a service with its own little NSQ, and then a thing that grabs its configuration. And we can put that into a Docker Compose YAML file. You can run that on your laptop. We can deploy that exact Compose YAML file to production with ECS. It's trivial. And it puts into the hands of developers everything they need to say, these are my runtime dependencies outside of things like my stateful stuff, like Postgres or whatever. So I would argue that we should just start saying you should support Docker Compose. And Kubernetes does this through a translation layer, where you give a tool that somebody wrote, thankfully, a Docker Compose file, and it emits a Kubernetes pod. Kubernetes pod, yeah. So Docker Compose, it's what devs need. So operations, and this is really the hardest part for me of adopting Docker, is that operations is really hard to begin with, and introducing all new operational difficulties has been a thing that has annoyed me a lot. So Docker, while supposedly being a panacea for developers and operations people and making it simple for everybody to do everything, fails to, by default, do anything responsible on a system. It doesn't solve operational problems. Its default configuration is absolutely not suitable for production. And its default configuration actually will continuously lead to downtime indefinitely. So by default, logging in Docker uses this little driver called JSON file, which allows you to do neat things like Docker logs on your laptop. The problem with this, well, we'll get to problems with this. There are a lot of problems with this. There's even tooling built around this fact. Glider Labs, Jeff Lindsay, he's a great guy, builds a lot of cool stuff, wrote Logspout, and it actually goes through the Docker logs API, it correlates, gets all the logs, and then sends them anywhere you want them to go. So the problem with this is that long-running containers will eventually consume all of the disk space for varlib Docker and eventually cause your machine and all of the services on it to fail in new and exciting ways. We ended up running etcd on the same cluster as the rest of our services, and etcd fell over in the middle of the night. And I was like, what's going on? I don't understand why it can't write to its wall log. And then I realized that disk was at 100%. And I was like, I thought we were beyond this. I thought disk was no longer a thing. So yeah, exactly. Why do we have disks? So, just don't use JSON file. Use syslog or AWS
But
log.
disks, right?
But disks, I know.
Yeah.
So yeah, like I said, this is Anna Kendrick, who I love. And she's very angry in this picture. And this is how I feel when I think about sensible defaults for something like Docker, because I think it should be part of the responsibility of any company to say, you know what, if we're going to say run us in production, why don't we make it so that when you deploy us, we're kind of at least sort of ready to go for production. So take responsibility. But this is also on operating system vendors, CoreOS, Debian, RHEL, Ubuntu,
Switches off a JSON
Fedora. Everybody uses JSON file by default. And everybody should maybe default to something more sensible for production, like just send it to syslog. Stop using JSON file, just send it to syslog. If it's going to journal D, I can pick it up somewhere. If it's going to a syslog file, at least I know it's getting rotated. This is not new stuff. And now I will breathe. And I will get off my high horse. Because I'm an angry ops guy. And yeah, that's my thing. We tried to make logspout work. We tried to do log rotation with JSON file, and it's just, there are problems that, I mean, we've tried to fix. We have pull requests merged to logspout. We tried to do everything we could with JSON file. Just because like setting up syslog is hard, and journal D doesn't do you any favors. Thanks, Leonard. So, you know, you're still running our syslog. You're still configuring syslog daemons. It's 2016, and I don't understand why. Disk problems. I use zip drives.
Identify that before you say what it is.
What's the capacity of this drive? It's 100 somethings. I don't know what. I don't care. I wasn't alive. So you need to manage your disk space very carefully. Still, you need to remove stale images. You need to kill stop containers. You need to get rid of all the layers that are there, and don't store tons of state locally. This is.
Do you have some answers for this? Because we do this constantly.
On startup,
your machine.
rm-rf varlib docker. So I did a search in Docker's GitHub repository, and there are hundreds of issues that say rm-rf varlib docker. And this is how you fix
Their graph database sucks.
Oh yeah, so this is the best part too.
Like, why are we using a new file system like some dude made up for no reason?
Because there's reasons. So this is the best part to me, is that I'm going to write Docker, and I'm going to say, you know what, by default, I'm going to just continuously write to this disk that I require for operation and maintaining my internal state, and eventually I'm going to fill the disk and then corrupt my internal state. And the only way that you can recover from this is rm-rf varlib docker. And, you know, I mean, okay, sure, fine. We will set up a systemd unit so that on startup we rm-rf varlib docker.
Hey, we've all used AMPP.
Yeah, exactly. Yes, yes. We all know what the amnesia database looks like under the hood. So we also have systemd units for this. Docker PSAQ, xargs, rm. Like, just remove all the dead containers. I don't even bother filtering. Just try and remove the running containers. I don't care. YOLO, right? And then just delete all the images I don't need. Like, why even bother? Just, no, really, this is.
But there's plenty of images. I don't know which versions of Docker you're using, but depending on which ones you're using, there's plenty that will actually have successfully somehow like mounted something it can't unmount, and then like just refuse to remove it.
That's why you rm-rf varlib docker when those eventually fill up your disk.
We'll show you our Docker GC unit when you're done.
So this is another big thing, and I'm really glad that Kubernetes and ECS push this, is memory allocation. So we have a JVM service that restarts daily because the JVM does not look at like the C group memory limit stuff. It just looks at, you know, the amount of memory that's available on the whole system, and it says, oh, well, by default, I'll just use this for my max heap. And then eventually it gets killed, and it just restarts, and that's fine. We've built to that at this point, but you know, you want to declare the resources you intend to use in that container, and then let the kernel kill it when they exceed that, read those resources, and that's good. But yeah, pick a schedule that supports this because it's really great. It helps you bin pack your containers on things better. It makes your neighbors a little bit more friendly, sort of. But yeah, the V8 runtime for Node and the JVM both just keep allocating heap until they get killed. Go doesn't adhere to resource limits either. It's just going to keep allocating stuff until it gets killed, and that's fine. Like, that's sort of, you know, Go's thing, and it'll be fine. It can get restarted. There's nothing wrong. But yeah, nothing adheres to these resource limits, and that's okay. It's meant to be that way. Your programming languages and your runtime shouldn't be an operating system, but you can configure most of them to at least not fall over and get killed by setting things responsibly, like, you know, max old gem size, max perm size, and things like that in the JVM. But yeah, don't forget also that, like heap isn't everything. You also have overhead for threads, etc. So, really be a little bit more generous than you need to with JVM and V8, and then limit lower, a bit lower than what you account for in your schedule. So yeah, anyway, sorry. Thanks for coming. To the people that aren't Worker or CoreOS or OPSI employees, especially, thank you. So yeah, any questions, comments? Nothing? What's up?
I have a question about that last bit you were talking about regarding memory allocation. Like, you have a process that starts in a container, and like, I was just wondering, how does it go beyond, what I don't understand is, how does it go beyond its like container memory limits?
Right, okay, so Go is, I think, the easiest example, because what'll happen is, let's say you're an irresponsible Go developer and you like to consume memory, right? And I mean, who isn't? So let's say I only need 32 megs of memory, right? Well, when the Go runtime hits its heap somewhere around 32 megs, it's going to try and malloc more heap for itself, and the kernel is going to say, nope, we're not going to do that, and Go will actually just crash. Like, your process will just crash.
I see.
Yeah. Or it'll cause like a garbage collection, and if it can't GC, then it will probably crash because you'll just die. Or it'll get killed eventually, right? So the problem with V8 and JVM is that by default they will say, I want more, I want all this, I want all of the memory on this machine. I mean, not really, they have limits, but on a T2 micro, they will say, I want all of the memory on
Hey,
this
dress
machine.
for the job you want to get,
Exactly. Always be thinking big. So they're going to try and allocate more and more memory, and then they're going to hit that wall again, just like Go will, right? Mm-hmm. And they're going to get killed. Like, they're just going to crash because they think they can allocate more memory. The allocation will fail, and then JVM and V8 both will just be like, okay, peace.
But what makes them think that?
Because the
kernel has like a resource limit for that process that it hasn't really checked on. So the process doesn't really know that it actually has been limited.
Exactly, because there's a disparity, right? So with Linux C groups, there's like this thing, this file system, the /sys file system, that you can inspect to see what your actual memory limit is. But if you look at the non-C group endpoint of that, you're going to end up getting the whole system's capacity. Or there's actually there's a syscall that you can make to find out how much memory you can allocate. And Linux will report the whole system, not the C group.
Oh, I see.
Yeah. So then the JVM starts up and it says, oh, well, my max heap is 4 gigs, but really you've only given it 256 megs.
Oh, wow.
Yeah. So yeah, V8 and JVM both do that, but there are command line arguments you can set that will make them adhere to those limits.
Can you tell them to ask the right?
No, you have to know the answer beforehand and tell them when you start them.
Yeah. And I think there's actually a pull request in the V8 runtime. I looked at this a while back. Like, we had problems with Node in a container, and I was like, well, what's going, I know I can set max heap, but like, why do I have to? Like, come on, figure this out for me, Brian Cantrell. But yeah, no, it doesn't. And there's a pull request somewhere, but I think it's just, languishing.
Thank you.
Yeah. Maybe good. P.S. If you want to try try OPSI, operators are standing by. Anytime.
Oh my god.